In this video, we're going to talk about implicit differentiation. So I've already referenced this a few times, but we want to really get into exactly what is going on with it now. So usually most of the cases that we've looked at so far, and functions in general, are defined explicitly, right? So this means when we say something's defined explicitly, we typically mean that our dependent variable, usually y, is all by itself on one side of the equation, right? So something like this, for example, and then maybe we call it f of x. This is defined explicitly. Okay, we're explicitly showing that y is a function of x. But what about something like, for example, the case of a circle? So in this case, it's, just at first glance, it's not really clear whether this is a function of x or a function of y, or, both. Like if there is a dependent variable or an independent variable. So we would say that this is defined implicitly. Okay. Hopefully I spelled that right. I did not. Let me fix that. So when we're talking about derivatives now, though, they still would make sense in this context. Now let's think just for a second, step back here, because normally we're talking about functions, and the way that we've defined this, this implicitly right here, there's no way to think of this as a function, right? This isn't a function. Specifically, this is the equation of a circle. And let me just show this, the graph of this right here on Desmos. So this is the unit circle. So the circle is centered at 0, 0, 0, and with radius 1. So this doesn't pass the definition of a function because it wouldn't pass the vertical line test, right? If you draw a vertical line anywhere on this function, or not function, anywhere on this equation, it would pass through 2 points, right? So it's not even a function in this context, but we can still talk about its derivatives. We just have to do it a little bit differently. And this is where the implicit differentiation comes in. So we might refer to this as a curve instead. So we'll talk about differentiating curves rather than functions. You'll catch a lot of sources still just calling these functions, even though they're really not. So you want to be a little bit careful about it, but if you come across a source, that calls something like this a function and says to take the derivative of the function or whatever, that might happen. I might say it myself a few times, as I already just did. But it is not technically a function, it is a curve. So we should talk about differentiating curves. So the idea of a derivative still makes sense. There's still a rate of change at each point, right? Now the difference here is that if we find the derivative at, say, x equals 1/2, you're going to get two different values, right? Because you'll get the derivative right here, which looks like it would be negative, I don't know, maybe like a fourth or something like that. And then you also have the derivative right here, which should be the same thing, but with the opposite sign. So maybe like 1/4, maybe a little bit more than that. But we'll go ahead and look at what that would be. So first, a little bit about how we would approach this. So y here is still thought to be a function of x, right? I said it's not really clear which is which, but usually we still go ahead and default to the y being the function of the other variable. But you could do it the other way and it wouldn't really make a difference. We just want to stick with one and be consistent. So we still think of y as being a function of x. So maybe I would rewrite this as x squared plus y of x squared equals 1. Okay. Now, the only reason I'm doing this and writing it this way, because we normally wouldn't, We normally don't write y of x at all. We write f of x, but this isn't a function. So, there's a little bit of a nuance here in that the whole thing is not a function, but we can still think of y being a function of x. It's really two different functions of x, all mixed into one. So now when we look at the chain rule, then this might start to make some sense here. So if we remember with the chain rule, if we had a function like this, we would basically take the derivative of the outside and then take the derivative of the inside, right? So let's take the derivative of this entire thing with respect to x, right? Or I should just say d dx. And we're going to do it on this side too. Maybe I'll move this over. So we're going to take the derivative of both sides here. Okay. Now this is something we haven't really seen because, again, we always had it defined explicitly, but we really were doing that the whole time. It's just that the right side was just y prime, or just the derivative of y, right? So now when we do it on the left side here, we get 2x. Because we're taking the derivative with respect to x, it's the same variable, so we don't have to worry about anything extra. Here, we're taking the derivative of a function of x, so we need to apply the chain rule. Okay, so this would be 2y of x times y prime of x. Okay, and now on the right side, it's the derivative of a constant, so we get 0. Now we can just go ahead and rewrite this. We don't need the y of x's anymore. I was just writing them there to show what exactly we're doing with the chain rule. We don't normally write it like that though. So this would just be something like dy y prime, or 2y y prime, or 2y maybe dy dx. Okay, and this is equal to 0. And then if you were looking for the derivative, right, this is the derivative of y with respect to x. So now we have an equation and we should try to get it by itself. Okay, so we bring the 2x over and then divide by 2y. So ultimately we're going to get dy dx equals negative 2x over 2y, which is negative x over y. Okay. So if we wanted to know the derivative at 1/2, for example, the rate of change of the curve at 1/2, then at x equals 1/2, well, notice that in our equation here, we also had to have to know what y is. Okay, so this is what makes these implicit curves a little bit different as well, is that now we have to actually figure out what y is if x is given a value. So x equaling 1/2 means that we have 1/2 squared plus y squared equals 1. 1/2 squared is 1/4. So this is y squared equals 3/4, because we do 1 minus 1/4 here, which is going to imply that y is equal to plus or minus root 3 over 2. Okay. So the plus or minus part is where, on the graph, we saw that at x, we of course have two different y values, right? And that's what's making it not a function. So we can go ahead and look at both of these points. Okay. So maybe you do something like dy dx of the point 1/2 root 3 over 2, or something like that. And then you could do negative 1/2 divided by root 3 over 2, which would be negative 1/2 times 2 over root 3. These cancel and you get negative 1 over root 3, or if you prefer the radical on the top, negative root 3 over 3. Okay. And then if you go ahead and plug in the negative root 3 over 2, I think it's clear that you're just going to get the same thing, but with a positive, right? So that's consistent with what we saw on the graph, that they look like they have the same rate of change, just with different signs. I said it was like 1/4, so a little bit off, but still just something between 0 and 1. That's really the best that you could really estimate here. So this basically, we have to go through this process whenever we're taking the derivative of something that's a function of a different variable. So just as an example, let's look at this problem where, here, let me copy the picture in here. So this is from a category of problems known as related rates, and it looks at different rates, which implies, that we have derivatives, and it looks at every variable being a function of time, right? Because rates are usually about time. So this says that we have a 10-foot ladder leaning against a wall, which we can see from the picture. It says if the top of the ladder slides down the wall at a rate of 2 feet per second, how fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall? Okay. So it's asking about an instantaneous rate of change, right? So the top of the ladder is sliding down the wall at a rate of 2 feet per second. So I don't know if I can draw on this picture. Yes, I can. Okay. So this is going down at 2. Let me move it over a little. Going down this way 2 feet per second. And we want to know how fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall. So when this is 5 feet from the wall, right? So the reason that we're going to need implicit differentiation here is that we're going to come up with an equation involving these variables, which is not going to have any time in it, but all of the variables we have will implicitly be functions of time. So they won't explicitly be defined as functions of time, but they will implicitly be defined as functions of time. So let's go ahead and look at where we would start here. So we first need to come up with some kind of equation that relates these three sides, right? So from the picture, we can see that the wall the ladder is leaning on, the ladder itself, and the ground all make up a triangle, right? So we can go ahead, maybe we'll call the bottom of this the base. The wall here we can call the height. And then we don't really need to give a name to this part necessarily, but because this one is not changing, it's just always 10, right? So notice what's happening here is that as the ladder slides down the wall, H is actually changing and B is going to be changing too. But the ladder height is not changing. That's always going to be a constant 10 feet. So from the Pythagorean theorem, we know that B squared plus H squared equals 10 squared. Okay. Now this is where the implicit part of this comes in, is that B is actually a function of time, right? Because this is moving at 2 feet per second. seconds being time. So as the time changes, b is changing, and same with h, right? So this is really b of t squared plus h of t squared equals 10 squared, which is 100. So again, this is where implicit differentiation comes in, is when you have a variable which is a function of a different variable, and that's what you're taking the derivative with respect to. So here we're going to want to look at the derivative with respect to time, because that tells us how the base is changing with respect to time and how the height is changing with respect to time. Okay. So let's go ahead and take the derivatives first. So I won't write the b of t out every time. We can just write 2b db dt. Okay, and you could just write b prime, but it's often written as with the fraction notation in this context, just so it's just so it's clear exactly what derivatives you're looking at. Plus 2h dh dt equals 0, right? The derivative of the right side is 0 because it's not changing at all. So the rate of change is 0, and because it's the derivative of a constant. So you could go ahead and divide everything by 2 real quick, just to cancel those out. So you end up with b db dt plus h dh dt. That's going to be an optional step, of course. You don't have to do it like that. So we want to know when the bottom of the ladder is 5 feet from the wall. In other words, when b is 5, what is db dt? Right? That's going to be this rate of change right here. We know dh dt is going to be -2. So note the negative here because it's going down. So the size of h is decreasing, right? H is decreasing, so the derivative is negative. B we expect to be positive, on the other hand. So we know dh dt. We know we're going to be looking for when b is 5. So the only other thing we need to know is what is h when b is 5. And we can find that out from the initial formula. Okay. So I'll just do that on the side here. If b equals 5, then we have 5 squared plus h squared equals 100. So h squared equals 75. So h is going to be 5 root 3, which is the square root of 75. So I'm just simplifying it a little bit here, but you could just leave it at as the square root of 75 as well if you want. Okay, so now we can go ahead and plug everything in. So b is 5. db dt is what we're looking for. H is 5 root 3. dh dt is -2. And this equals 0. So this is going to be -10 root 3. So we're going to get 5 dB dt equals 10 root 3. Divide both sides by 5. And finally we get dB dt is equal to 2 root 3. Right? And it's going to be in feet per second here if you want to put the units on there. So all of these related rates problems are kind of the same process where you come up with some initial equation to relate all of the variables that's implicitly defined as functions of time. And then you do implicit differentiation to get the derivatives in there. Usually one of the derivatives are given to you and so on. All right, so we get 2 root 3 feet per second. You could put that in a calculator if you want the decimal answer. So that tells us that when this is 5 feet away from the wall, the instantaneous rate of change of b is 2 root 3. Okay. So again, I just want to emphasize real quick the difference with something being implicitly defined. Okay. So in something like this, x squared plus y squared equals 1, y is implicitly okay. I'm going to write 2 functions of x. Okay. So implicitly, y is a function of x. Y is actually, in this case, plus or minus the square root of 1 minus x squared. So 2 different functions of x. So that's why we usually refer to it as a curve or something like that, because it's actually 2 functions and not a function overall. But this is different from something like f of xy equals x squared plus y squared. So this is a function of 2 variables, and this is what you would look at in multivariable calculus, right? Which would be the subject of Math Tools 3. So this is going to be a little different here. You could still implicitly differentiate it. Like you could still take the derivative with respect to time or something. But if you're taking the derivative with respect to x in this context, you would just get 2x. Okay. So the y variable in that case would just go away. You treat it as a constant. So that's because in this context, in the second one, y is not a function of x. So that's making all the difference here. In the first context, y is a function of x. It's just defined implicitly instead of explicitly. Here we explicitly have a function of 2 variables. Y is not a function of x. So when you take the derivative, it just goes away.